All right, welcome back, everyone. Grab your detective hats because today we're on a scientific investigation. We're going to uncover a super cool hidden property of matter, something that's literally all around us, in everything from a simple party balloon to the tires on your bike. Ready? Let's get into it.
So think about it. What's really the difference between the air you're breathing right now and a glass of water? I mean, yeah, one's a gas, one's a liquid. Obvious, right? But what does that actually mean? Well, we're about to find out with a super simple experiment that's going to show a huge difference in how they act when you put the squeeze on them.
Okay, every great detective needs their kit, right? For this mystery, our tools are super simple. You probably even have this stuff lying around the house. And that's it. Seriously, just a small syringe, some regular old water, and a beaker. With just these three things, we are totally going to crack this case of compressibility wide open.
All right, let's open our first case file. Subject number 1, air. We're going to see what happens when we put it under a little bit of pressure. Let's go gather that first piece of evidence.
Okay, so the steps are super easy. First, just pull the piston, that's the plunger part, all the way out. That fills the syringe with air. Got it? Good. Now, block the little hole at the end, the nozzle, really firmly with your thumb. Don't let anything escape. And now, for the moment of truth, try to push that piston back in. Go on, give it a push.
Whoa, look at that. Check out our evidence log. When you push on the piston, it actually moves. See that? It doesn't go all the way down, of course, but it for sure moves inward.
Okay, let's log that observation. This is a big one. The air inside that syringe could be squeezed. It could be pushed into a smaller space. That, my friends, is a major clue.
All right, quick knowledge check. So what does this first clue tell us about the air inside that syringe? If you can squeeze it, what does that mean about all the little air particles? It kind of suggests they're not all jammed together, right? There must be some empty space in there.
Okay, on to our next suspect. Let's open case file number 2 and see if it acts the same way. We're going to run the exact same test, but this time with water.
Okay, let's do this again. Fill up the syringe with water this time. Try to get all the air bubbles out. Now, once again, seal that nozzle tight with your thumb. And, just like we did with the air, give that piston a good push. Try to squeeze it.
Whoa, okay, check out this piece of evidence. No matter how hard you push, that piston is not moving, not even a little bit. It's totally stuck. Wow, that is a completely different result from our air test.
So let's log our second observation. The piston did not move. It looks like water really doesn't like to be squeezed.
Time for another knowledge check. Think about this. The air could be squeezed, but the water couldn't. So what do you think that tells us about how the tiny particles in water are arranged compared to the particles in air?
All right, detectives, we have all our evidence. We've got our clues from the air test and our clues from the water test, and they are pointing in very different directions. I think it's time to put it all together and solve this mystery.
Okay, let's lay it all out on the table. With the air, the piston moved. We could squeeze it. With the water, the piston did not move. We couldn't squeeze it. This shows us a huge fundamental difference between a gas and a liquid.
And this special property, this ability to be squeezed, actually has a scientific name. It's called compressibility. It's basically just a fancy word for how much you can shrink something down by putting pressure on it. That little syringe experiment we just did, that was a perfect test for compressibility.
So, the mystery is solved. Gases, like air, are compressible. Why? Because all their little particles are really far apart, with tons of empty space in between. But liquids, like water, are not compressible, because their particles are already snuggled up super close together. There's no room to squeeze them any tighter. And with that, case closed.
And now, the investigation continues with you. You're the detective now. Think about it. When you squeeze a party balloon, you're literally compressing the air inside. But try squeezing a water balloon. It doesn't really get smaller, does it? It just squishes around. Or what about a sponge? When it's dry, it's full of air, and you can squish it flat. But once it's soaked with water, it's much harder to compress. So my challenge to you is, where else do you see this in your daily life? Keep your detective eyes open.